Alright, so we're going to work some problems using the boiling point elevation and freezing point depression constants, okay? Now remember, with our freezing point depression constant, I put a little negative in there to remind us that it is a depression. So we're going to have to subtract it from the original freezing point in order to get our new freezing point. Okay? So let's go ahead and do a problem. Here we've got, I'm going to pull out the information as I come to it as I'm reading the problem. 275 grams of ethylene glycol. So we have 275 grams. I'm just going to abbreviate this EG, ethylene glycol, per 100 grams. So it's per 100 grams of the water. Okay. And it's in the car radiator. What will be the freezing point of the solution? Okay. So we need it in moles per 1,000 grams in order to plug it in here. So not a problem. We know how to change grams to moles. Remember, the amount of water we're not changing. We're only changing the ethylene glycol. Maybe I'll write down the water here so we'll remember not to change that one. So we were given the molecular mass of ethylene glycol. We can figure that out from our periodic table, but it was nice that it was given to us. We've got grams in the top, so where do grams have to be to cancel out? Well, they have to be in the bottom. So we've got 62.1 grams per mole of our ethylene glycol. Grams is going to cancel out, and that's going to give us our moles of ethylene glycol that we have. 275 times 1 divided by 62.1. So we've got 4.43 moles of ethylene glycol per 1,000 grams, 1,000 grams of water. Note, I did not divide by the 1,000. Okay, I just took the 275 and divided by the 62.1 because over here we need it per 1,000 grams. Okay, so that's different than what we've always done it. So do make sure, don't divide by that 1,000 because we need the 1,000 down there. Okay. Now we'll go ahead and plug it into this formula for our change in temperature. Remember, we're calculating the change in temperature of the freezing point, not the actual freezing point. So we've got our constant, 1.86 degrees Celsius per mole 1,000 grams, times our actual number here is 4.43 moles of our ethylene glycol per 1,000 grams, times our I. Now I we need for our compound. Now this is a molecular compound. So it's held together by covalent bonds. We know that because these are all nonmetals. So the I of every single molecular compound is what? It's 1. We're going to multiply it by our 1. And you'll notice that the moles of 1,000 kg, or 1,000 G, is going to cancel out with our moles of 1,000 G. So we don't actually type the 1,000 into our calculator at any time. Okay? They cancel out. So what we're typing into our calculator is 1.86 times 4.43. And we should get 8.24 degrees Celsius. Remember, that is our delta T sub F. It's a change in the freezing point. So if we want to know the actual freezing point of water, and you just do this calculation, I'm going to have to take some points off. Because that's not the actual freezing point of water. Not with that calculation. I want you to actually show me the next step. Because if it's anything but water, it's not going to be the same number. Now with water, the freezing point of water, the normal freezing point is what? 0 degrees Celsius. And then we're going to subtract our 8.24 degrees Celsius. So we do get negative 8.24 degrees Celsius. That is the same number as this, but only because we're using water. So I want you to show me this last step so that I know that you're thinking about it. If it's any other substance other than water, you're going to have to subtract it from the original number, the original freezing point, in order to get that final freezing point. And if it's the boiling point, you're definitely going to have to add whatever you come out from this calculation to the 100, which is your boiling point of water. So don't forget this last step. Let's go ahead and do another one where it's not so straightforward. This one was straightforward in the fact that it was given to us per 1,000 grams. Here we've got one that's not per 1,000 grams, so we're going to have to calculate that into our situation. So here we've got what is the freezing point of the new solution prepared by dissolving. We've got 53.3 grams of K2SO4. But at this time it is in 4,000 grams of water. Okay. So let's work it. I'm going to work this one a little differently to see if the way I work the other one works for you, then do it that way. If the way I do it here works for you, then do it this way, okay? And I'm going to give you two different views so that you can see different ways of thinking about it. Here we know that we've got this much solute in this much solvent. So what we're going to do is we're going to just focus in on getting that solute to moles. We're not going to put it over a fraction. In fact, for the time being, let's leave that out, okay, just to make things a little more clear. We're just going to get this into moles, okay? So here we know we can use our molar mass to do that. Grams on the top, where do they have to be to cancel out? They have to be on the bottom. 174.27 grams per mole. We're just changing the grams to moles. So we take our 53.3 and we're going to divide it by 174.27. And we get 0.306 moles. Now that we have it in moles, now we're going to worry about the volume of the liquid. Okay? So we have 0.306 moles in 4,000 grams of water. We know for a calculation we need it in per gram of water. A little bit of a reflection here. Let me see if I can adjust that. So what we're going to do is we're just going to divide both of these, the top and the bottom, by 1/4. Okay? That's going to give us, divide 3.06 by 4, we should get 0.0765 moles in 1,000 grams of water. This is the form we need to plug right into there. Okay? That's what that is. So now we can go ahead and use this equation and plug right into there. Our delta T of the freezing point equals our negative 1.86 degrees Celsius per, remember these are just units, moles per 1,000 G. We're not actually going to divide by 1,000. We're going to multiply by the number we got here, 0.0765 moles per 1,000 Gs. The moles per 1,000 Gs here cancels out the moles per 1,000 Gs there. Don't forget we have to multiply it by I, times I. Now our compound is K2SO4. So when that goes into water, what's it going to do? Let me get it back here so you can see it. We have two K's, pluses, and we're going to have one SO4. So that's 3 particles. So our I is 3. So we're going to multiply it by 3. Let's go ahead and do that math. and we get 0.427 degrees Celsius. Again, to get the final freezing point, we have to take our normal freezing point, which is 0 degrees Celsius, subtract out our change in our temperature, and we're going to get our final freezing point. Don't forget this last step. It tells me you know that you're going to have to subtract it from the normal freezing point. Now, sometimes it gets confusing because some of the numbers go up, some of the numbers go down. So I like this analogy that I'm going to show you guys here. It's also on your slides. But we've got this little alligator. The one on the slides is much cuter. My drawing's not quite as good as the one on the slides. But you can imagine that this alligator is opening its mouth. Okay? So the boiling point goes up, the freezing point goes down. Boiling point elevation, freezing point depression. Okay? Another way to look at it is this is our basic picture with no solute. We have the solid, we're going to have the freezing point, that's the temperature at which it turns into a liquid. Then we're going to have the boiling point, that's the temperature at which it turns into a gas, right? So this is our normal picture of our three states of matter. When we add a solute, what's going to happen is it's going to want to stay in liquid form longer. It's going to want to stay in the liquid state longer. So both of these are going to go further away from each other so that we have it in liquid state longer. So adding a solute really benefits that liquid state. So that's another way you can remember that boiling point goes up, freezing point goes down, because you're trying to keep it in liquid state longer. Okay? So use those to help you remember which way the trends are for boiling point elevation, freezing point depression.